The last polar shape is polar roses, and remember that the names of the polar shapes have given an indication what the picture is going to look like, but in this case, roses is a very loose word we use for flowers. And when I say flowers, I mean like I used to draw them back in elementary school, where all the petals came back to the middle, like that. So that's what our polar roses are going to look like. So keep that in mind as we go into this. Now, polar roses are completely different from any of the other polar shapes, which should make the equations easier to spot, but that means we actually need to do the summary before we begin an example. So if you look at the format for the polar rose equations, you're going to have a single term, but that single term will have two numbers in it. It's going to have a coefficient out in front of it, and that will tell you the length of each petal. And then it's also going to have a coefficient in front of theta inside the trig function, so that there's a little invisible set of parentheses right around these things right here. They're both inside the trig function. And that's going to control how many petals we will have. If n is an odd number, then it tells you exactly the number of petals you're going to have on your rose. And if n is an even number, then you're going to have twice as many petals as that on the rose. So this first example that we're going to look at is going to end up becoming a rose that's got 4 petals, because we're doubling the 2 that's in front of the theta, and they're each going to have a length of 6. And then what we do is we only generate actually essentially half of one petal. And so what we do is we locate the tip of that first petal. That'll tell us the location, kind of like knowing where this is. And what we're going to do is, because we have an even number of petals, we're going to generate this petal and this petal. And we're going to generate 2 points that tell us how fat or skinny the petal is. So they're going to be 2 points that kind of look like that. Because these petals are very, very symmetric. There's symmetry everywhere. These petals are symmetric over, each petal has its own little axis, and so this side of the petal will end up folding over on this side of the petal. They'll also have rotational symmetry around the 360 degrees of the circle, and they'll have axis symmetry. But the axis symmetry can't help you locate the graph all of the time, so you can't count on that. And you'll see what I'm talking about on I believe the last example of these notes. So sine has a maximum at 90 degrees. The trick is that doesn't mean that we're going to plug 90 degrees in. What we're actually going to do is we're going to plug 45 degrees in, because our equation has a 2 in front of the theta. So what that means is that when I plug 45 degrees in to my equation, I end up evaluating sine of 90 degrees, which is what I was aiming for, because sine of 90 degrees is the largest possible sine value of 1. And so we get a final answer of 6. So what that means is that I got an answer of 6, but when I plugged in 45 degrees. So that tells me where the tip of the second petal is, or the first petal. 1, 2, 3, 4, 5, 6. So right out here, there's the tip at 45 degrees, 6 units out. And then sine has a minimum at 270. So what angle would we need to plug in so that when we doubled it in the equation, we would be evaluating 270 degrees? And hopefully you're thinking, or you said 135. So we plug in 135, so that way when we double it, we're evaluating sine of 270 degrees, which is, hopefully you said -1. And so we end up with an answer of -6 at 135 degrees. And so we're going to rotate towards 135 but head 6 units away from it. which puts us right out here. So we've now located the first two tips of our petals, and we can now technically locate the other two if you want to go ahead and do that. But usually what we do is we generate one whole petal, and then we just reflect that petal over and over and over again. Okay, so we have plotted these first 2 points, and now the next thing to do is to determine how fat or skinny each petal is going to be. For those petals, the width of the petals, you plug in whatever angles would be necessary to give you 30 and 60, just those two. So as far as number crunching goes, the roses are only ever going to consist of finding either 3 or 4 numbers, and then the rest of this graph is entirely symmetry. So the theta that we would need to plug in to be evaluating 30 degrees in this particular equation is 15 degrees because of the 2 in the equation. And so we're going to evaluate r is equal to 6 sine of 2 times that, which gives us 6 sine of 30 degrees. And of course, sine of 30 degrees is 1/2, and so we get an answer of 3. So that means we're going to put the point 3, 15 degrees on our graph. 1, 2, 3, 15 degrees would be halfway in between 0 and 30, right there. And then the theta that we would plug in to evaluate 60 degrees would be 30, actually. So r equals 6 sine of 2 times 30 degrees. So we're evaluating sine of 60, and sine of 60 is square root of 3 over 2. And so we end up with 3 square root of 3. Now, when we graph it, obviously we'll need to decimal approximate that. So remember, we give you the decimal values. Square root of 3 is approximately 1.7. Tripling it is approximately 5.1. So 5.1 would put it somewhere right around here. So what we have is we have the bottom half of that first petal. Didn't locate the tip very well. So we know all of our petals are attached to the pole, and they're going to swing through those 3 points that we have. We're going to take those 3 points and we're going to mirror image them across the tip. Remember, there's this little invisible line of symmetry across the tip of each petal right down here. And so I'm going to take my tip as obviously my point of reflection. This point at 5.1 was, I always count grid lines, or you can count degrees. It was 15 degrees, or 1.5 grid lines, away from the tip. So I'm going to go 1.5 grid lines in the other direction. That would put it over here. And then this one down here at 15 degrees, that was, 30 degrees away from our tip. And it was, so we're going to go 30 degrees in the other direction and rotate around to right there, if I can get it to draw. And so what I've got is I've got my, it's pegged down at the pole, swings through the 3 points I calculated, comes back around through their mirror images. Okay, and so now let's see if I can plot the other points without having to approximate so much, because it's hard on a grid this small. So we had already located this tip right here. All the points are going to look exactly alike. So remember that the 2 points that were at 5.1 were 15 degrees, or 1.5 grid lines away from our tip. So I'm going to go 1.5 grid lines in each direction and go down to 5.1, right about there, and right about there. And then the ones that were 30 degrees apart were down at 3. So 1, 2, third ring, 30 degrees away from our tip, the tip of our petal. Right there, and about right there. So I start at the pole, I swing out through those points, and there we go. So I now have 2 complete petals. Okay, and I'll take a picture of the finished product in pen so you can see what it should look like when it's actually graphed on paper, because it's, like I said, it's hard to graph with a grid this small. And then the other 2 petals, because I know I'm supposed to have 4 petals, are going to have y-axis symmetry because my equation had sine in it. So if I know where these 2 petals are, then I simply reflect them across the y-axis, and I'll have the other 2 petals. So I want you to pause it. I want you to generate those remaining 2 petals, and then I'll take a picture and show you what it should look like on paper so that you have a better idea. Okay, so this is the picture of what you should have generated. Hopefully you paused it, and you can see that the points are obviously much easier to plot on paper than on the screen. But we have a 4-petal rose. The tips go 6 units out, and they all anchor at the pole. And we determined the thickness of it using this point, and this point. And so that's what determined how fat or skinny each of our petals were. And then we simply took our petals and reflected them across the y-axis. So the final example is going to be a rose. It's going to have 3 petals with a length of 5 each. And that's because in this case, n is odd. And so when we had that 3 theta in our equation, we didn't have to double the 3. 3 is the number of petals. Now this is one example of when your axis symmetry is not going to help you locate petals, and that's because this particular example has cosine in it. Cosine's got a maximum at 0, so that means the tip of our first petal is going to be located right on the x-axis, and so trying to use it to reflect across an axis to locate the other petals is not going to help us. But that's okay because these roses also have other kinds of symmetry. So because we have an odd number of petals, we only need to locate the maximum point. So theta would need to be 0 degrees, so that when I plug it into my equation, I'm still evaluating 0 degrees. So 3 times 0 degrees is, of course, still 0. And cosine of 0 is, of course, still 1. And so we're going to put the tip of our first petal 5 units out towards 0 degrees. So 1, 2, 3, 4, 5. Okay, and then the next step says to go ahead and generate your 30 and your 60. I'm not going to go ahead and jump down there because then I would have to jump right back to the graph. I'm going to go ahead and do these here, and I may need to jump up to the top here for a little bit of empty space. But what would theta need to be so that when I plugged it into the equation, I was evaluating cosine of 30 degrees? Hopefully you said 10, or you're thinking 10 degrees. So when I plug that into my equation, I have r equals 5 times cosine of 3 times my angle, and of course 3 times that is the cosine of 30 degrees I was looking for. And cosine of 30 degrees is square root of 3 over 2. And so I end up with 5 times square root of 3 over 2. And remember that once again, the square root of 3 over 2, you can approximate it 0.9, 0.8, anywhere in between. I'm going to shoot for 0.9 again because it is closer to 0.9 times 5. So we're looking at approximately 4.5, just shy. You always want to err on the side of being shy of it, at 10 degrees. And so I'm going to plot that. And the nice thing is that it's on a grid line. So 1, 2, 3, 4, just shy of 4.5. So right somewhere right around there. And then I'm going to jump up here and I'm going to plug in 20 degrees. So that I can do 5 times cosine of 3 times 20 degrees. which is cosine of 60 degrees, which is 1/2. So I get a nice exact answer, 2.5 at 20 degrees. So 1, 2 and a half. And so this time around I've got the top half of my petal right there. And I'm going to go ahead and I'm going to reflect across the tip of the petal so that I can go ahead and finish this petal off. So one grid line below for the, approximately 4.5-ish, and then 2 grid lines below for the 2.5, so right around there. And so there's the first petal. And so then, now the trick is that I need to locate the other petals. I can't use my x-axis symmetry, even though cosine is in the equation. I can't use it to locate the other petals. Now I'm going to see that x-axis symmetry in my finished product. It's not like it doesn't have it, but it doesn't help me locate it. But I know there's going to be 3 petals, and everything about this rose is going to be symmetric. So if there are 360 degrees in a circle, then that means that these are going to be equally spaced at 120 degrees apart. So I'm going to take this point right here and I'm going to rotate it around to 120. And then I'm going to rotate it around again to 240. So there's the tips of my other 2 petals, and now they will have the same exact size and shape as the first petal. So 1 grid line away at just shy of 4.5, and then 2 grid lines away at 2.5. So here and here. So there's another petal. And then 1 grid line away at about 4.5, and 2.5 at 2 grid lines away. And so there's my third and final petal. And so now I can see, yes, I do have x-axis symmetry because cosine was in the equation. This petal folds over itself on the x-axis, and then this petal right here folds over on top of this petal right here. So I can see it, I just couldn't use it to draw the graph. Okay, and the first rose that we did actually did have the same symmetry. It had the same rotational symmetry. If you look at it, we had 4 petals over 360 degrees, and they ended up being 90 degrees apart. But we don't use that rotational symmetry to locate the other petals. You could have just done this one and then started 90 degrees apart to generate the other 3. But we didn't have to use that because of the fact that we had sine in the equation, and that gave us our y-axis symmetry. We weren't sitting right on an axis. So that's your final polar shape, is the roses. And so ask questions in class, and we're going to give you more practice to do in class later this week.